Welcome everybody to the last instructional video on complex numbers. There are two videos to follow containing exam questions, exercises for complex numbers, but this here will be the last thorough explanation of the basic material. So this here is actually a pretty nice conclusion to the chapter on complex numbers because we're learning how to solve special algebraic equations over the complex numbers. We start with a well-known example. Here the ordinary quadratic equation with real coefficients x squared minus 2x plus 2 equals 0. I think you all know what to do. You would use the quadratic formula, in German the Mitternachtsformel or Midnightsformula, because our students have to learn it by heart so that when you wake them up at midnight they have to be able to tell you this formula. So if you apply the quadratic formula here, you see that under the square root there remains a negative number. So in ordinary school math we make this lightning symbol here and say this is not possible, because obviously you cannot take square roots of negative numbers. But now over the complex numbers we can. So we already know that the square root of minus 4 is actually 2i, because 2i squared is minus 4 and 2i lies in the upper half plane. So without any problems, this equation now has two solutions over the complex numbers, one plus I and one minus I. Good exercise to plug these into this equation and actually check that they are indeed solutions, and that we didn't do anything illegal or wrong. And now the good news is that actually every quadratic equation with arbitrary complex coefficients, even, not only real coefficients but complex coefficients, with a not being equal to 0 of course, because then it wouldn't be a quadratic equation. This equation here always has solutions over the complex numbers, and they are given by our well-known quadratic formula, except that now a, b and c are complex numbers instead of real numbers. And this proposition actually is a special case of the famous and celebrated fundamental theorem of algebra that is way beyond the scope of these videos to prove. But the funny thing that is bothering algebraists up to this day is that there is no proof that is purely algebraic. Every known proof actually uses at least a little bit of analysis. So this fundamental theorem of algebra states that every equation of this form, every polynomial equation with coefficients in the complex numbers, I forgot to write that down here, always has solutions. So this here is a special case for n equals 2. Now for n equal to 3 or 4, there actually are formulas, the well-known, the famous Cardano formulas, which are a mess to write down. Well, for 3 it's alright, for 4 it's not so pretty anymore. And for n equals 5 or larger, one can actually prove that it is impossible to find a formula of this form containing plus, minus, multiplication, division and roots of any form. This is a famous theorem by Abel that quintic and higher equations cannot be solved by so-called radicals. This also is of course way beyond the scope of these videos, but it shows you that this here is an existence theorem. It doesn't tell you how to find the solutions for n equal or larger than 5, but it tells you there are solutions. And this is often very useful in math, to know that there are solutions if you can, even if you can't compute them using such formulas. Okay, but I digress. Now back to this quadratic stuff here. The proof of this quadratic formula actually carries over verbatim as over the real numbers, because all you need are the field axioms and the ability to draw square roots. So if you have never seen the proof for the quadratic formula before, now is a good time to actually think about this proof. We start by completing the square, in German quadratische Ergänzung. So we start out with the left-hand side. Now see we do not alter, but here we pull out the a, so that here we have z squared and here we have b over a times z. And now I want to produce a complete square. So I have to divide this guy here by 2 and square it, because now the red terms form a complete square. This is what I want to have, but of course this would be wrong, so I have to subtract b over 2a squared, which is this guy here, b squared over 4a. And now I can easily solve the equation for this term here. I bring these to the other side. I divide by a. Remember, a is not 0. And so this here can be written as, if I bring it on the common denominator, b squared minus 4ac divided by 4a squared. And now comes the important step. We know from our last videos that every complex number has a square root. Or put slightly differently, every equation of the form something squared equals a complex number always has at least one solution. If here this side is not 0, then it has exactly 2 solutions. And this is the big difference to the real numbers. Here, this step in the complex numbers is always possible. In the real numbers, it is not always possible. So I know that here I find 2 solutions. I call these z sub 1 and z sub 2. And these are given by the square root of this number here, plus and minus, because I always have 2 solutions if this here is not 0. And now, of course, the square root of 4a squared is 2a. A little technical difficulty would be that the square root is defined as the arrow lying in the upper half plane. But here we do not have to worry about that because we already have a plus or a minus. So it doesn't matter at all which arrow we take for the square root. And then I can solve for c1, z sub 1 and z sub 2. I simply bring this to the other side, and then finally I write it as one fraction, and that's it. That is the proof of the famous quadratic formula. As I said before, it's the same as over the real numbers, with this exception here that it always works. Now, simple application. You are given this quadratic equation, now here with a clearly complex coefficient for c. So we have, this here is b, and this guy here is c, and a is 1. So we simply have to apply the quadratic formula, like so. Now simplifying the term under the square root gives you 12 minus 16i. Now I can pull out the number 4, leaving me 3 minus 4i under the square root and pulling out the 4 as a 2. Then I can cancel the 2's and I'm left with this expression. And now you have to be able to actually take the complex square root of this here without a calculator. This was done in exercise 9.17. Please refer to this video if you're not sure how to do this. And then you find that the square root of this number is minus 2 plus I. And then you obtain the 2 different solutions of this quadratic equation given by minus 1 plus I and 3 minus I. And that's about it. And if this is an exam question, then of course this has to be so friendly that you must be able to actually find the square root without the use of a calculator. Okay, and to conclude, we are going to solve this equation here leading to the so-called nth roots of unity. A complex number raised to the nth power, n of course being a natural number. And this, to avoid the trivial case 0, we take as a non-zero complex number, and we are going to see that this equation always has n different solutions. So we start with the case n is equal to 3 and c is 1. So we want to solve the equation z to the third power equals 1. Now, of course, a trivial solution would be 1. And in the real numbers, this actually would be the onlyest solution of this equation. But over the complex numbers, we find 2 more solutions. Because you see, if you take e to the 2 pi over 3, simply this number here written in the denominator times I, then if I raise this to the third power, here I get 3 times this guy here, which gives me 2 pi I, and e to the 2 pi I is nothing but 1. So this here is another solution, and we call this one here zeta sub 1. Small Greek letter zeta. Have fun trying to write it. That's a bit awkward in the beginning. And this is called a third root of unity, because if I raise it to the third power, I get 1. Now this picture here clearly shows you what is happening. The complex number 1, so this arrow clearly is a solution, trivial solution of this equation. Now if I rotate this arrow by 2 pi over 3 or 120 degrees, I end up with another arrow that, when raised to the third power, again gives me 1. Why? Because this angle here times 3 gives me 2 pi. So I end up with e to the 2 pi I, which is nothing but 1. And then, of course, rotating by another 2 pi over 3, all in all, altogether 240 degrees, gives me the third solution, here denoted by zeta sub 2. And these 3 solutions, zeta sub 1, zeta sub 2, which is nothing but zeta 1 squared, because by squaring this arrow I simply double its angle, giving me this here, and zeta sub 3, which is this guy to the third power, which is nothing but the number 1. So I call this zeta sub 3. Another possibility would be to call this here zeta sub 0. So I start with e to the 0I, which of course is 1. This depends on your taste, whichever you prefer. And these 3 solutions of this equation here are called the third roots of unity. And they divide the unit circle into 3 points. The endpoints of these arrows here give you an equilateral triangle, gleichseitiges Dreieck, or a regular trigon. Because for n equals to 4 or larger, it is not the same being equilateral or regular. Regular meaning same side length and same angles inside. So for n equals to 4, equilateral fourgon would be a square, or a, I don't know the English word, Raute. So I'll show it to you here. This guy, for example, would be an equilateral fourgon, but of course not regular, because not all the angles are 90 degrees. So now it's easy to generalize this result here. If I have the equation z to the nth power equals 1, n being an arbitrary natural number, then I can see that this equation has exactly n complex solutions called the nth roots of unity. And they are very easy to obtain. You start with e to the 2 pi divided by this n times I, and then you simply take all the multiples of this angle here, k running from 1 to n or from 0 to n minus 1, whichever you prefer. And then, if necessary, you can use Euler's formula and write this here in Cartesian form with the cosine and the sine of these angles here as the real and the imaginary parts. And there actually is nothing left to prove, because if I take this to the nth power, the n cancels and I'm left with e to the k 2 pi I, which is k times fully around the unit circle, so I always end up with 1, and obviously they are all different. No two of these guys here for k equals to 1, for k between 1 and n are the same. And of course they form an regular n-gon, because the angle is always 2 pi divided by n. I start out with this, then I double the angle, I triple the angle, and so on. So I end up dividing the unit circle into n equal pieces. That's why this is called in German Kreisteilungsgleichung. I haven't found the English term. Unit circle division equation sounds wrong. And now with this in mind, it's very easy to solve equations where the right-hand side is an arbitrary complex number. So equations of this form. And I ran out of space here. It's easy to prove that also this equation here has exactly n different complex solutions. And I'll show you the principle using this example here. We want to solve z to the 4th power equals minus I. So not 1, but minus I. The solutions for z to the 4th power equals to 1 are given here in blue, and with the dotted line that would be a square in the unit circle. But now we have to include the fact that here is not 1, but minus I. The first step is always to write the right-hand side in polar form. Minus I is the arrow pointing downwards. So the angle is 270 degrees, or 3 pi over 2, and the length is 1. And now it's very, very easy to obtain the first solution of this equation. You simply take the 4th real root of the length. This is easy because in this case the length is 1. So you have 1 here, and you simply divide this angle by 4. So 3 pi over 8 times I. And this is a solution because if you raise this to the 4th power, you exactly end up with this here, which is minus I. So, and now comes the trick. You simply have to multiply this first solution, which I call W for German Wurzel, root. You simply have to multiply this W by all the roots of unity. In this case, the 4th roots of unity. Because all these guys are solutions. Take a look. Zk to the 4th power is zeta k times w to the 4th power. Now using the power rules, this is zeta k to the 4th power times w to the 4th power. But zeta k to the 4th power, of course, is 1 because we have the roots of unity. They always give you 1 when you raise them to the nth power. And w to the 4th power is by construction simply minus I. That's how we started out. So all these here are solutions of this equation. They are obviously different because they have different angles. And this here is an equation of order 4, and this can't have more than 4 solutions. Proof exactly as over the real numbers. Polynomial of degree 4 cannot have more than 4 roots or zeros. So we have found all the solutions of this equation. To write them down explicitly, you simply have to multiply this w, this guy here, with all the 4 different roots of unity. In our notation here, the fourth root of unity is 1, so our 4th solution is simply w itself, this here. And the others are simply rotated by 90 degrees because 2 pi over 4 is pi over 2 or 90 degrees. So all we are doing here is rotating the square that corresponds to z to the 4 equals 1 by 3 pi over 8. We simply multiply all the roots of unity by w, and that's it. Now this is maybe a bit messy because of the many colors. I'll show you again. On the left-hand side, the square corresponding to the 4th roots of unity, where I would have a 1 here. And no, in this direction here. Here you have the rotated square, simply rotated by this solution W. And this is the trick how you solve any equation of this form. You bring the right-hand side into polar form, you take the nth root of the modulus and divide the angle by n, and then all you have to do is simply multiply this one solution by the nth roots of unity. And that's it. Whew, okay, this concludes our journey into the basic facts about complex numbers. I hope it was enjoyable and helpful to you. Thanks for watching, thanks for your support. Bye bye.